In this course, we're building a totally modular asteroid game in Godot 4.4.1, where everything from the player ship to the weapons and even the asteroids are made up of small reusable components that you can mix, match, and even expand. And yes, to answer a question that may be on your mind, this is kind of like killing an ant with a steamroller here, because there are a lot easier ways to make an asteroid-style game. But we're not just making a game. We're learning how to design scalable, flexible systems that can grow with your ideas. Using a really simple game like Asteroids makes it easier to grasp the concepts, since the game mechanics and gameplay loops involved are small enough so that we can focus on learning the way composition and decoupling works. Let's get started. Let's make some changes to the project settings. Go to Project, Project Settings, and in the Display section, go to Window. I will change the viewport height and width to be 960 by 540. The input field supports calculations, so I chose this size because it's half the size of 1920 by 1080, which was 1920 divided into 2 and 1080 divided into 2. Now, this will be the game window size, so later when we upload the game to itch.io, it won't be too big for the web. Then I checked Always on Top. Now, since this window is really small for the game view in the editor, I can override the window size to be the original 1920 by 1080. Then I change the stretch mode to canvas items, then click Close. And I think this will be all the setup we need for now. Players control a spaceship in open space, shooting and dodging increasingly chaotic waves of asteroids and enemies. This style of game is perfect for showcasing composition and decoupling in Godot. Well, the game is built from repeating modular behaviors. Let me explain. Asteroids break into smaller pieces, power-ups spawn, and enemies behave independently. Each game object, like an asteroid, enemy, bullet, or power-up, can be built from independent components like movement, collision, destruction, scoring, or visual effects. This makes it easy to mix and match logic, test paths in isolation, and build complex interactions without tangled code. By using composition and decoupling, we can create clean, reusable systems that scale. At the top right, we have the Scene tab. This is where we will be creating the various nodes that we will use to make up our game. And below this is the file system. This is where we can import files that we'll be using into the engine. So here I have a folder with the art assets that I will be using. I created the art using Inkscape, and all the art assets are 256 by 256 pixels. For the color palette, I used the Grape Soda color palette from lowspec.com. To import the art assets, all we need to do is drag the art folder into the file system in Godot. With the art in the engine, let's make the player character. First, click on Other Node and search for a character body 2D. Create it. And rename it to something like Player Ship. We're using this node because it's a physics-based body that we can fully control with a script. Next, this node needs a collision shape 2D, so it can interact with other objects. Click the plus icon, search for collision shape 2D, and add a new circle shape as its shape. Now let's add the visuals. With the player ship node selected, click the plus icon again and add an animated sprite 2D. This will display the player ship and handle its animations. In the Sprites Frame tab, rename the default animation to idle, then drag one frame to use for the idle animation. In the inspector, scale it down to around 0.3 so that it fits better on the screen. But you might notice the collision shape is no longer visible. That's because it's being rendered below the sprite. To fix that, just drag the animated sprite 2D above the collision shape 2D node in the scene tree. Now you'll see the collision shape clearly, and you can adjust its size to fit nicely over the player ship. Now would be a great time to save the player scene. simply click on File and then Save, or use Ctrl+S to save. In the window that pops up, click on the Add New Folder button on the top right and give a name for the folder. I called it Scenes. Click OK and then Save. Next, we add an empty node as a child of the player ship and rename it to Abilities. Then add another empty node as a child of the Abilities node and call it Move Ability. With the player ship node selected, click on the Add Script button to add a script to the player ship. I will call it Player Ship. Then we create a new folder called Scripts and save the player ship script there. Then just add the scripts to the other empty nodes and rename them. I call the scripts Abilities and Move Ability and save them in the Scripts folder as well. So this is how we will use composition here. Imagine this. We have the player ship that's like a spaceship toy that we want to fly around and do stuff. Then we have the Abilities script. This is like a remote controller box that we can attach gadgets to. This will make the plane do the stuff we want to do. And then the actual gadgets, like the Move Ability and Shoot Ability, which has the actual instructions to perform the stuff we want to do. Because the ship just follows what its gadgets say, you can just pop out the Move Ability and snap in a new gadget like a Dash Ability, or even pop in a Shield Ability without rewriting the ship itself. So here's how the abilities.gd and player.gd scripts work together. Let's start with the abilities script that extends Node2D. We can use the class name keyword and assign the script a class name abilities. Inside the physics process, it loops through all of its children and checks if they have a method called processAbility. If they do, it calls that method and passes in delta. The processAbility is a method that we'll create that will have the ability logic. That means we can add any number of ability scripts like moving, shooting, dashing, or shielding as children of this node, and they'll run automatically if they implement a processAbility function. No need to hard code them into the player. Now, over in the player.gd script, it extends character body 2D, and we have an exported variable called abilities, which expects a reference to an abilities class. In the player's physics process function, we just call abilities.physicsProcess and pass in delta. So what's happening here? The player script delegates ability behavior to this separate abilities node, which then delegates to its own children. Instead of the player script knowing about every possible ability, it just lets the ability script handle it. This setup keeps the player script clean and makes it super easy to plug in or remove functionality without touching the core player logic. And lastly, we call move and collide and pass in velocity. Okay, you could also use move and slide, but I chose move and collide because in Godot, move and slide is great for platformer style movement. It handles things like gravity, friction, and sliding automatically. Imagine a character sliding on ice or walking up slopes. But for a space game like my version of Asteroids, in my opinion, move and collide is a better fit. It gives you more precise control by detecting exactly when and what your ship hits, without adding unwanted behaviors like sliding or gravity. And since space movement is free-floating and frictionless, and you want specific reactions when objects collide, like destroying the player on impact, move and collide is the ideal choice. It keeps the physics simple, accurate, and responsive for this kind of gameplay. Now let's quickly set up a forward animation for the player. To do this, in the player scene with the player animated sprite selected, I go to the Sprites Frame tab and click the Add New Animation button. Call the animation forward, then drag in the sprite frames for the animations. Then set looping to on. And that will be all I need to do for the animations for now. Before we start adding the abilities, let's quickly discuss how we'll control the player in the game. In the classic game Asteroids, the basic player controls involve rotating the ship left and right using directional buttons, moving forward with a thrust button, and firing using a shoot button. In my version, in addition to these core controls, I've also added a reverse ability that could be toggled on and off in code. I will map this ability to the S key and the down arrow keys respectively. I know that this goes against the classic controls, but I thought that it could add some more depth to the gameplay, and it could be toggled on and off for a short time or attached to a separate fuel gauge that can be filled with a pickup if you choose to use this ability in the game. The left and right rotation would be mapped to the A and D keys and the arrow keys respectively, and the thrust to the W key and up arrow. And as a plus, I would also like to add controller support for the game and map the thrust and reverse thrust input to the triggers on the controller. Now that we understand the mechanics behind the movement, let's take a look at the movability input and script. First, let's add the player input. We go to Project, Project Settings, Input Map. Then add the name for the action. Let's start with Turn Left. Then click the plus button to add an event. And now we could either search manually for the event input in the list, or at this point, the editor is now listening for input. We could just press the key on the keyboard or the button on the controller to add the input event. I will press the A key on the keyboard. This will set Turn Left input to the A key. Then click OK. Then click the plus button again and add the left arrow key and click OK. For the controller, click the plus button one last time, and since I'm using a PS4 controller that's connected to my PC using Bluetooth, all I have to do is move the left analog stick on the PS4 controller to the left and the input is entered. Then click OK. And then repeat this process for the rest of the input events on the keyboard and the controller. Now things start getting interesting. Let's take a look at setting up the movement with the move ability script. I will set up constants for acceleration, deceleration, max speed, and rotation speed. These will all be statically typed as floats. Why constants? Well, these values will not be changed at any time during the gameplay, so they can be assigned as constants. Next, I will need exported variables for the input actions we created, and assign them the type string, and set a default input for each action. Let's break this down. At export, this makes the variable visible and editable in the Godot inspector, so you can change it from the editor without modifying the script. var forward action declares a new variable named forward action. Semicolon string specifies that the variable must always be a type string, like forward, reverse, turn left, or turn right. Equal forward sets the default value of the variable to forward in this example. Then we create an exported variable canReverse and assign it the type bool, which can either be true or false, and set its default value to false. We will use this to handle if the player is allowed to use reverse input. Next, I create an @export variable called player that expects a reference to a node of type characterBody2D. This makes it show up in the inspector, so I can drag the actual player node into it, and it lets the script manipulate the characterBody2D node. Then an exported variable called playerSprite that expects a reference to a node of type animatedSprite2D. This holds a reference to the animatedSprite2D node. I will use this to change the player's animations like idle, move, shoot, etc. based on the player's movement or input. And lastly, I create an @onReady variable for screen size and assign it the type vector2 and set it equal to player.getViewportRect.size. It's okay to do this because we will not be changing the viewport size dynamically during runtime, and we are assigning the screen size directly from a node's property. Player.getViewportRect.size returns the dimension, width and height of the viewport that the player node is currently in, and that property likely depends on the scene being fully initialized. We will use the viewport size to handle the wraparound function of the player movement later on in the script. Now let's take a look at the processability function in the movement script. This is the function that the player depends on to handle the movability logic. First up, I check if the player is pressing the keys to rotate the ship. If the rotate left action is pressed, I rotate the ship counterclockwise. If the rotate right action is pressed, I rotate the ship clockwise. I multiply the rotation speed by delta, the frame time, to make sure that the rotation is smooth and frame rate independent. Next, I handle thrust. Basically, when the player is trying to move forward or backward, I set up a thrust variable to track the input strength and a thrusting flag to know if I'm actively applying thrust. If the player presses the forward key, I play the forward animation on the ship's sprite and increase the thrust. If not, I switch to the idle animation. I also check if the player is allowed to reverse based on a can reverse flag. If so, and the reverse key is pressed, I subtract from the thrust value, letting the ship move backwards too. Now, if the ship is thrusting, we figure out which direction it should go by rotating a right pointing vector based on the ship's current rotation. We then add a force to the ship's velocity in that direction, scaled by thrust, acceleration, and frame time. If the ship isn't thrusting, we apply deceleration, basically slowing the ship down gradually. If it's still moving a bit, we slowly move its velocity towards 0. And if it's almost up, we just set the velocity equal to 0. Finally, we make sure the ship doesn't go too fast. If the velocity exceeds the maximum speed, we scale it back down to that limit by normalizing it, which keeps the direction but caps the magnitude. In the original version of the wraparound code, the player's global position is checked manually to see if it has gone off the screen. If the X position is less than 0, meaning the player moved off the left edge, it's set to the screen's width, making the player reappear on the right. Similarly, if the X position is greater than the screen's width off the right edge, it wraps to 0, the left side. The same logic applies to the Y direction. If the player goes off the top or the bottom of the screen, their Y position is reset to the opposite edge. This method works, but involves multiple if and else if statements, which can get repetitive and clutter the code. The refactored version simplifies this logic using the built-in wrapf function. Instead of manually checking boundaries, it wraps the player's X and Y position within a range using one line. Wrapf global position.x 00 screen size.x for X and similarly for Y. This function automatically keeps a value within a range by looping it around when it goes out of bounds, which is perfect for screen wrapping. The result is cleaner, more concise code that's easier to read and less prone to errors. It removes the need for multiple conditional statements, making it a best practice choice for this feature. Now let's set up a game scene so that we can test the player. First, we'll need to assign the ability script in the inspector for the player. Then we create a new 2D scene. I will rename it to Game and save the scene. When we run the game for the first time, Godot will ask us to choose a scene to be the default scene, and we can just click OK to choose the current scene. Now all we have to do is drag the player scene into the game scene. And just like that, we have a player that can move around and wraps around to the opposite side of the screen in the classic Asteroids fashion. Let's start work on the shot. Here's a breakdown of the scene. At the very top, we have an Area 2D node as the root node, because an Area 2D node is perfect for detecting overlaps in 2D space. Exactly what I want for bullets or projectiles. It is also perfect since I will not be using physics forces to move it around like the player. I will just be tracking where it goes and checking if it hits something. Underneath the single shot, there's a shot sprite, which is a sprite 2D node. This is the visual representation of the shot. It's what the player will actually see. Then, as a child of the single shot, there's a collision-shaped 2D node. This defines the hitbox for the shot, essentially the invisible area around the shot that checks if the shot made contact with another object in the game. Now with the single shot selected, I can go over to the inspector and in the Node tab, click the plus button to add a new group and give it a name, Shots. This icon here means it belongs to a group. A group in Godot is a way to organize and tag nodes so you can easily find or interact with them in code all at once, even if they're in different parts of your scene tree. Think of it like putting a sticky note on the shot that says, you belong to the group Shots. And later I can say, okay, everyone with this sticky note, do this thing. Not to worry, This will all make sense later. And now I add a new script called shots to handle the shots logic. This script extends area 2D. At the top, two constants are defined. Speed, which sets how fast the bullet moves, in this case 400 pixels per second, and lifetime, which determines how long the bullet exists in the game, in this case 1.5 seconds, before I remove it from the scene. There's also a screen size variable to store the size of the screen so that the bullet can wrap around the edges. And lastly, a velocity variable that uses a vector2 and sets it to vector2.0, making sure it has a 0 value before any movement logic is applied. Ready gets called when the shot enters the scene. It first grabs the screen size using getViewportRect.size. Then it figures out which direction it should travel by rotating a base vector, vector2.right, using the bullet's current rotation. I used vector2.right because when I created the shot, I made it face the right. This ensures that no matter which way the player is facing when they shoot, the bullet will fly in that direction. Finally, I create a timer using getTree.createTimer and pass in the lifetime, so that after 1.5 seconds, the bullet automatically deletes itself with cue-free. This prevents bullets from flying around forever and cluttering up the game. Now, inside the func physics process delta, which runs every frame, the bullet's position is updated by moving it along its velocity, direction, and speed, multiplied by the frame time. This ensures smooth frame rate independent movement. To add screen wrapping so the bullet doesn't disappear if it leaves the screen, the bullet's global position is wrapped using wrapF as we did for the player. So if it goes off one edge, it reappears on the opposite side. This gives that asteroid style endless space feel. Well, I think this would be a good point to pause the video for now. We already have the basic idea of how composition and decoupling work by setting up our player. In the next video, we'll take a look at using these principles to create the asteroids. We'll use composition to create an asteroid script that expects the asteroid's behavior class, which looks for the process behavior function that will handle all the behavior of the asteroids. We will also look at how we can spawn the asteroids in the game, break the asteroids into smaller parts, and score points. Thanks for joining me in this series. If you like what you saw so far, why not subscribe and turn on notifications so you can join me for part 2. And while you're here, why not check out one of my other videos like this one that's kind of like an introduction to how composition and decoupling works in Godot. But you know what? I would really love to hear what you think of the series so far. So until next time, happy coding and I'll see you in the comments. This has been Deragu Games.